Hey, what's up everyone and welcome to Daily Code Buffer. This is the second video of the series for system design called Scalable Thinking. In the previous video, we understand about the hashing algorithm, that is the consistent hashing, where to implement and how we implement it. In today's video, we are going to learn the new technique that is called the Bloom filter. So we are going to learn about what is Bloom filter, where to use Bloom filter, and how we can implement Bloom filter in our tech stack. So without further wasting any time, let's understand how to implement a Bloom filter. So first of all, where we can use the Bloom filter. Suppose if you have a requirement where you have billions of strings available and you want to search the values within those strings. So suppose if you have ABC and you have billions of strings available and you want to search if ABC is available within the huge strings or not, then what you can do is you can do a hash set. Okay, so let me just show you that as well. So suppose if you have 1 billion strings, okay, and what you have done is you have stored everything in a hash set, right? So that's how we store the value, where we can store all those unique strings within a hash set, and whenever we want to search that if that particular string is available or not, what we do is we check within this hash set that okay, if ABC is available or not. If it's available, it will send that value with true. If not, it will say that the data is not available, and simple. So what it will do is it will tell that if data is available, true or false. Okay, very particularly it will say, but the time complexity to do this would be O of n in the worst case, right? Because we know that how hash set stores the data. Hash set stores the data into an array, right? It will store the data into an array, and each array will have a linked list. So suppose if any of the element is at the last point of a linked list, and if all the data is stored in only one bucket, then the worst case scenario would be O of n, where it will take that much time to search the data for me. The same goes for insertion as well. So the worst case will be O of n, but probability in the realistic time you will get the data in much faster ways as well. Is there anything that is much faster than that and we can get the data in a constant time? Yes, that's the Bloom filter, where we will get the addition of the data, where we will be able to add the data or search the data in constant time. So that's where we can have the Bloom filter implemented. So this is the requirement where I want to search with the billions of string and I want to have that searching in a constant time rather than the of n or linear time. So in that case, we can use a Bloom filter. Now let's understand how Bloom filter is implemented. So what Bloom filter will do is, Bloom filter will store an array. So it's an array data structure. So I'm just creating an array from 0 to n, and this data structure, this array would be of bits. Okay, 0, 1 bits. That's it. And what will happen is, what it will do is, suppose I want to store some elements. So suppose I want to store color red. Okay, what it will do is, to store the value red, we cannot directly store because it's a bit structure, it's an array of bit, so we can only store the data in terms of bit. We cannot directly store red. So what we will do is, we will take this red and we will pass this red into an hash function. Okay, now this hash function can be of multiple hash functions. Suppose if I just use one hash function, then it will return only one value, and if I just store that particular one value, suppose here, then it's just one value, and if something else comes up, suppose blue, and blue also turns out to be the same value, then it will be very difficult to identify that it was red or blue, right? So what we will do is, we will make sure that we pass this red through multiple of hash functions. So suppose I am passing this hash function for 3 times. Okay, so red will pass for 3 times and it gave me the value, 3 values. Okay, one I placed it as here, one I placed it at here, and one I placed it at here. So now you can see that 0, 1, 2, 3, 4, 5, 6 and 7. So I have an array of 8 here, and you can see that the value of red is stored in first position, second position and third position. Okay, so now this is how I have stored the value with the help of 3 hash functions. Now suppose I want to store green. Okay. Now for green, I'm storing the data as 2, year 1 again and year 1 again. Okay. That's it. So that's what I'm storing the data for green as well. So you can see that the data which I'm getting, I'm passing through hash functions, a series of hash functions, and whatever the values I'm getting, I'm just putting that values within the bucket itself here. Okay, so this is a bucket, and whatever the value, whatever the hash value that I get, I am just storing that value. Okay, so now you can see that while storing the data, okay, as we are directly storing in an array, the addition of the data within my bit array is a constant time, because for every value I'm just using the same constant time to insert the data. Now what about search? Suppose I want to search. Okay, so search, suppose I want to search for red. So while searching, again I will pass through the same hash functions 3 times. Okay, and it will give me 3 values, that is the again 1, 3 and 5. So what it will check is that, okay, whatever the values that I'm searching at all those places, if the value is 1 or not, if the bit is present or not. If I get all those values, then it will say that, okay, data is present. Simple. Okay, if I search for green, okay, for green also it will go and check that, okay, I will pass this green value with 3 hash functions again, and it will find that, okay, it's available at this position, this position and this position. Again we will get the same values, and at all those places I will check that, okay, I have all the bits present as 1. That means the value is present. Okay, now I will search for maybe purple. Now purple is been passed to 3 hash functions again to search the values. Purple is not available here. Okay, so what I will check is I will get the 3 values here from this hash function. Suppose one value is year, one value is year, and one value is year. So for all those 3 positions, I will check what is the value of a bit. So here I got 1, here I got 1, but here I got as a 0 because 1 is not present. So any of the values in the array, if we get as a 0, that means that that particular value is not present. So it should return as false. Okay, so it's simple thing. So that means that if any of the bit is present as 0, that means that value is not present, and it will firmly say that the value is not present. But if all the values are present, it will say that the value is true. Now suppose if I check for the value, suppose I'm checking for the value something like this orange. Okay, now orange is returning again 1, 2 and 3. These are the 3 positions. Okay, now you can say that I will go and check for these 3 positions, that is 1 is present as 1, yes, I have a bit. 2 is present as bit, yes, bit is present as 2 position as well. At 3 position also the bit is present, but I have never stored orange in this particular array. So that means that this particular return true though the data was not present in my array. So that means that this particular Bloom filter will probabilistic say that the value is present. Okay, so it does not guarantee every time the value would be present, so it can also return false positive answers. Okay, but it will never return a false negative answer. So if any of the bit is not present, it will definitely say that this value is not present, but sometimes false positives may occur, and if the data is not present, it may end up saying that the data is present. So these are the functions of an Bloom filter, that it will be very efficient. It's a very efficient algorithm. As you can see that we are not storing a complete data, we are not storing a complete data, we are just storing the bits of it. So it's very efficient in storing and retrieving the data. So it will be almost of an big O of 1, that is a constant time. The next thread is that it can send the false positive. So if we are okay to get some false positive within the data structure, then we can use this Bloom filter, and it will always say no if data is not present. So that means we will never get false negative. If data is not present, it will firmly say that data is not present, but if data is present, then it will probabilistic say that it might be present in the data structure. Okay, so yes is always a might, that it might be present, but it's a firm no always. So that's the trade-off that we have from the Bloom filter, that it will probabilistic say that the data might be present, but it will firmly say that the data is not present. So this is how the data structure is implemented. You can see that it's very simple. We just have a bit of array, and within that bit of array we just store the bits of the data. And how we store the bits? We do the hash function, and based on the hash function we get a list of different values and we store in the data structure. Now where this particular data structure has been used? Now this particular data structure is been used in many ways. If you want to just search the data if the data is present or not. So if you want to just search the data if the data is present or not, then at that time we can use this data structure. Suppose if you want to check if the cache value is present or not, at the time we can use this data structure. If the cache is present, then you go to fetch the cache, because it will just lower the overhead to get the data from the cache as well. It has also been used in the fraud detection system. It has been also used to identify malicious actors as well. So Google Chrome uses this particular technology to identify if the particular URL is malicious or not. If it's malicious, if it's probabilistic, say that if it's malicious, then it will go and check the actual URL in the database if the value is malicious or not. Because every time we go and check the value in a database, it will take a too much overhead within the system. So we'll always go with the probabilistic structure. If it might be present, then we can go and check actual way. This is also used to check the password strength as well, to check if the probabilistic way that the password is meeting the criteria or not. If it's not meeting, then we say firmly no. If it's meeting the criteria probabilistic way, then we can say yes. If it's not meeting, we can always go and check within the server as well. So we are reducing a lot of overhead within our system using the Bloom filters. So these are many ways that we can use Bloom filters, and as an engineer you should know that how Bloom filter works, because this is a very old algorithm. It's been there for ages now. So understanding this is really important. So you can see that it's very easy to implement. Okay, you can see that it was very simple to understand and implement, and if you go through the code as well, it will be very easy, but it's very powerful algorithm. So what I will show you is I will go through the code and let's see how this can be implemented. So let's go to IntelliJ IDEA and let's see how we can implement this in Java. So here you can see that I have created a class called Bloom filter, and what I have used is I have used a bit set. Bit set is nothing but an increasing data structure where we can store the bits values, and it will increase the length according to the requirement. Okay. So here you can see that what we are using is we are using two values here while creating the Bloom filter. That is the size we are taking, what is the size that we want to create, and how many hash functions that you want to use. Okay, now these two things depends based on the requirements and based on the function that you are building. Okay, how many hash functions you want to use and what is the size of the array as well. Okay, and you can see we have also used the seed value. Now seed value is very important to use when we are working with the hashing. We have seen the seed value in the consistent hashing algorithm as well. Here also seed value is very important to make sure that we add a constant value to our value, whatever the hash function that we are using, to make sure that we are getting an even distribution of the data. If you are not adding a seed value to our values, then what will happen is it will create a hotspot in one of the areas. Okay, so we add a seed value, and that will make sure that we are getting an even distribution of the data within our data structure. So that's why we are using a seed value here as well, and you can see seed value is nothing but a random value here. Okay, so now let's go and check with the add value function here. So what add is doing is it's taking a data here, and with that data it is getting the list of hash values. Okay, so if we go to this hash values function, what it is doing is it's taking the data here, and what it is doing is it's creating an integer array of the hash values. This hash number is something that we have passed. Suppose 3, 5, 7, whatever the number of hash values that we want to use, we can pass it on. Okay, so it will create an array, and what it is doing is for each and every array value it is creating a hash code, and it is using the seed value to create a hash value. Okay, now this particular hashing algorithm, you can use anything. We just need to make sure that we are getting a unique values here to avoid a collision, and it should be a rare collisions example. Okay, so we need to make sure that there is a very less collision happening, and that's why we have to make sure that our hash algorithm is efficient enough. So that's what we are. This is a very simple algorithm that has been used, that whatever the values we are getting, string value, we are getting the hash code of it, and we are doing an XOR operation with a seed value that we are getting. Okay, so for 0 we are doing seed into 1. If it's value 2, then we are doing seed into 2. For third value we are doing seed into 3. Similarly what we are doing here. Okay, so once we get the hash value, what we are doing is we are dividing it, or modulo, we are doing a modulo operator on a bit size array. So if we have a size of 100, then we are doing a modulo operator so that we can get a index where we can put that bit set. Okay, that's what it simply is doing. This is something that we did in the consistent hashing as well. So once we get the values, 3 values, what we will do is we'll put in a bit set. Simple. Similar thing, we have created a might contain function because it's a probabilistic data structure where we might get the value or we will firmly say that the value is not available. So with this data, we will do the same thing again. We will get the hash values, and for each hash values, we will check what is the bit set value. If the bit set value is not present anywhere, then we'll definitely say that the value is not present. If we don't find that, if the bit value is not present, then we will say that it might be present. It's a simple thing. Okay, so you can see that it's very simple. If I run this algorithm as well, okay, you can see that within the Bloom filter we have added hello world and we checked for hello world in Java. So first two, you can see that we got true that the value is available, but for Java it got value is not available. Okay, now you can see that this is only handling for 1000 of data available. Okay, if I want to handle for tens of millions of data, then I have created one more class as an optimized Bloom filter, and here you can see that what changes I have done. I have just changed the number of hash functions here. Okay, so now I am passing more number of hash functions, so I'll get more number of bits to place in my bit set array. And what is the size? The size also I have increased of a Bloom filter or a array. Now the only change here I have done is I have used a murmur hash algorithm instead of just getting the hash value directly, and I have, you can see that this is the murmur hash that I have used, and the hash function seed values also I have used separately. So I'm getting the data here, and with that data I'm just creating the integer array out of it. So if it's 7, it will create a array of 7 values and it will convert my data into byte array. Now for this byte array, what I'm trying to do is with the murmur hash function, I'm passing the byte array and I am passing the seed value as well. We saw that earlier, seed value is very important to make sure that we get a even distribution. So this is the seed value, this is the hexadecimal seed value that we have provided, and these are the standard seed values. If you go through the different algorithms, you will see that these are the standard seed values provided. Now you may ask, what are the seed values? This seed value is nothing but an fast inverse algorithm, fast inverse square root algorithm. Okay, so if you want to get the inverse square root of any of the numbers, then you need to go through the bunch of operations. So what it's been identified that if you pass this value, it will get you the probabilistic value or very near value to that fast inverse square root. So it will be very fast, so you don't have to compute a lot of resources. So the value is directly being used. And so you can see that first time we are doing this one hash function. The second time we are doing again a hash function, but with a different seed value. This seed value is a seed value being used in the murmur hash algorithm, and this is a magic number that's been identified to make sure that there is a very less collision and probabilistic even distribution of the data. Okay, so if you Google it, you will get these values. It's very easy to identify, and this is what you can directly use in your algorithms. So you can see that it's very simple thing that we are doing. Okay, for every hash function, what we are doing is we are getting the hash value with the absolute values of first hash function plus I into hash 2. Okay, and we are doing again modulo of bit size array. So we'll get the exact indices where we can store the values. Now this is the only important thing that you have to identify based on your requirement. If you are also using the standard hash function, so this is a standard hash function. If you implement this, this should be good enough for you for most of the cases. Okay, so once you implement, the rest of the things will remain the same. There will be no change in it. It will just work as it is what we saw in the Bloom filter. So if we run this as well, you'll be able to get the data very quickly that 2 are true, that is the hello in world, and Java is false. Okay, so it's simple thing. So this is how you implement Bloom filter in Java. You can change your language as well, you can implement accordingly, but the idea remains the same, where you need to create a hash function such a way that you get an even distribution of data and you store all of those data in a bit array. That's it. Now this is a Bloom filter we implemented for a single node, but we need to make sure that this Bloom filter, wherever we implement, that should not be a single point of failure. Every component that we build should not be a single point of failure for us in our distributed system. So how we can make sure that this is a distributed structure for us? Okay, so what we can do is we have a multiple ways to implement as in a distributed way. So what we can do is we can have a partition Bloom filter. So what we can do is, if we have multiple nodes available, for all those multiple nodes we can partition that Bloom filter, and all those different parts of the Bloom filter can be there in the different nodes available. So now when we do this, we have, suppose, different partitions available, right? So different partitions available in the different nodes available. So it's n1 node, n2 node, n3 node. So whenever you want to add anything or search anything, what you have to do is you have to search in all those places, right? So you can divide across these partitions into different nodes, but the only challenge you will get is that when you are searching for it, you have to search in all those different nodes, and while searching through all those different nodes, it will add a latency as well and a complexity as well to search in all the nodes to fetch the data. So if you want to really distribute the Bloom filter, you can easily distribute using the partitioning system, but it will add a latency to it. So that's the catch here. Okay, the second one we can do is the replicated Bloom filter. Okay, now in replicated Bloom filter, what will happen is it will replicate the Bloom filter whatever we created into multiple nodes. Okay, so we need to make sure that whenever we are implementing this replication in the different nodes, we need to make sure that the replication is being handled very seamlessly, because replicating the data into different nodes also will take time, and all the requests coming to that particular nodes has to fetch the data from that replicated instance of the Bloom filter. So now with this replicated Bloom filter, the advantage for us will be like, it will be very efficient, it will be super fast to fetch data in the replicated form, as all of the nodes will have their own instance of the Bloom filter. The only drawback from this replicated Bloom filter is that the probability of getting the false positive may increase, because if I have added some data in node 1 and if that data is not present in node 2, then the probability of me getting a false positive will increase in that scenario. So that's how the Bloom filter for replicated partition will work, and that's the drawback of the replicated partition. Counted Bloom filter. So by default, when we create a Bloom filter, the main characteristics of the Bloom filter is that you cannot change the data. Once you have added the data, you cannot change it. But if you have any requirement that you want to change the data, and you want to make sure that whenever the data is being changed, you want to increase or decrease the data, at that time we can use the counted Bloom filter. Now what counted Bloom filter will do is, rather than just storing the bits, you can store the integer of array, and you can keep on increasing the number of values or integers that you store. So first time when you are inserting, you add 1, second time when you are inserting, add 2, and so on. Now the disadvantage of this counted Bloom filter will be, it will use more space, because bit array will be using only in bits, and integer will store more values within the data structure, and it will consume more memory, and the operation will not be that much efficient as well. So ideally, counted Bloom filter will not be used in much scenarios. So mainly if you see, replicated Bloom filter and partition Bloom filter are readily been used in the industry. Now if you are aware about Redis, Redis has its own implementation of Redis Bloom. Now Redis Bloom is by default data structure available in Redis, which helps to do the same thing. It's a Bloom filter. So if you are working in a distributed system and you want to implement a Bloom filter, you can by default go ahead with a Redis Bloom filter and you can implement it. It's very easy to implement. You can just give what's the size you want and what's the percentage of error false positive you can bear with. Once you do it, it will replicate your Bloom filter across multiple nodes, and you will be very fast to fetch the data from the Redis Bloom filter. You can also implement the same thing using the Kafka as well, where you can stream the data across multiple publishers and consumers, where whenever there is a change in your Bloom filter, you just publish those events and rest of the consumers can consume those events to fetch the latest state of the Bloom filter. So these are the different ways that you can implement Bloom filter, and the most easiest way and the most widely used within the industry is using the Redis Bloom. So this is how you can implement Redis Bloom filter within your system. If you enjoy this video, then give us a thumbs up and subscribe to my channel for the upcoming videos. You can also click the join button below to support my channel. If you have any doubts regarding any of the things that we have covered, then we can have a discussion in the discussion forum in the comment section below. I will see you in the next video. Till then, happy coding. Bye bye.